Chapter 4, Applications of the Derivative, 4.3, Graphing Functions. You may need to pause the video more often than usual. We will follow the guidelines set out by your book. Except for one place in 5 and 6, I will break from the guidelines. Otherwise, I will stay true to the list. Analyze the function and then graph it. Domain. The denominator is 0 at 1 and -1. Symmetry. F of -x equals negative f of x. So our function has symmetry about the origin. First and second derivative. Start the first derivative using the quotient rule. Take the individual derivatives, multiply, combine like terms, and factor. Second derivative. Quotient rule, individual derivatives, factor x squared minus 1. Cancel identical factor in the numerator and the denominator. Multiply, multiply and distribute the negative. Combine like terms, factor. We have accomplished our goal of finding the first and second derivative in factored form. Critical points and possible inflection points. A critical point occurs where the derivative does not exist or where the derivative equals 0. This derivative does not exist at 1 or -1. However, those 2 points are not in the domain of the function, so we do not call them critical. We also have possible critical points where the derivative equals 0. The derivative equals 0 when x is equal to 0, radical 3, and negative radical 3. We have a possible inflection point at x equals 0 because x equals 0 makes f double prime equal to 0. Find where the function is increasing or decreasing. To do that, we use the first derivative, the critical points, and the domain. We use the domain and the critical points to break up the real number line into intervals. On each interval, we need to determine if f prime is positive or negative. Notice that 10x squared and x squared minus 1 quantity squared are both positive. The only factor left is x squared minus 3. So the sign of the first derivative depends on the sign of x squared minus 3. So we ask ourselves, where is x squared minus 3 positive, and where is it negative? X squared minus 3 is positive beyond negative radical 3 and beyond positive radical 3. And it's negative in between those 2 points. So the function is increasing up to negative radical 3 and beyond radical 3. And it's decreasing everywhere else. Find extreme values. We have a relative max at negative radical 3 and a relative min at positive radical 3. Even though x equals 0 is a critical point, it is neither a max nor a min. Find where the function is concave up and concave down. For concavity, we use the second derivative. Use the domain and the possible inflection point to break up the real number line into intervals. On each interval, we analyze the sign of f double prime. On the first interval, f double prime is negative, and so the function is concave down. On the second interval, the function is concave up, and then concave down, and then concave up again. Find any inflection point. We have an inflection point at x equals 0. -1 and 1 are places where the concavity changes. However, we do not call those inflection points because they are not in the domain. Locate asymptotes and determine end behavior. A vertical asymptote occurs where, with a rational function anyhow, a vertical asymptote occurs where the numerator is, let me start again. The vertical asymptote occurs where the denominator equals 0 and the numerator is non-zero, and that occurs at 1 and -1. So we have a vertical asymptote at 1 and -1. What about end behavior? For that, we look at the degree of the numerator and the denominator. The degree of the numerator is greater than the degree of the denominator, Also, the numerator and the denominator are both positive when x is large. So as x goes to infinity, the function goes to infinity. And after radical 3, the function will just continue to grow and grow and grow. How about the other end? Again, since the degree of the numerator is greater than the degree of the denominator, we know the end behavior is either plus or minus infinity. This time, when x is very negative, the numerator is very negative and the denominator is positive. So the overall ratio is negative. And as x goes to negative infinity, the function goes to negative infinity. And so after negative radical 3 going off to the left, the function will continue to get more and more negative. Intercepts. The y-intercept is at 0, 0. We look for other possible x-intercepts, and we find none. So 0, 0 is the only x-intercept. So the entire graph has only one intercept, 0, 0. Choose an appropriate graphing window and make a graph. To do that, we're going to plot a few points. Certainly we want to plot the relative max and relative min. We want to know how high they go so that we make our y-axes tall enough and negative enough. We also want to make sure we get all of the x points of interest. So we're going to want radical 3, we're going to want 1, we're going to want negative 1, we're going to want all of those x values to be included, as well as the y values of the max and the relative max and relative min. So it looks like a window negative 3 to 3 by negative 40 to 40 will suffice. If you are graphing by hand, you will want more points than these 3. As you graph, use the analysis to guide you. We've got symmetry, increasing, decreasing, concavity, relative max and min, inflection, intercept, end behavior, and vertical asymptotes. When you are done, it will look something like this. Note the local max and min. Notice the inflection point. Notice the vertical asymptotes and the end behavior. Notice concavity and where the function is increasing and decreasing. Notice the x and y-intercept, and that the graph only crosses the x-axis once. Notice the symmetry about the origin. Take care. Have a great day.